This talk is a joint work with my colleagues from Brazil, and this is actually a generalization of previous work on the cases of the groups UN, spin 7, and some others as well. So we try to put together a general approach to this question of harmonicity. So this project of harmonic theory and harmonic factory. Before I forget the Bretagne assumption, all my manifold will be clean, everything will be smooth. You all know about harmony, we learned about this in a couple of talks already. You move around the vectors, gadgets and goals around the closed path, and then you measure the deviation from the original vector, and that gives you a group. And in 1955, Berger proved that if you take out under these assumptions, so it's probably a product and they are not symmetric manifolds, then there's only 7 cases. In fact, 8, because the last one I'm saying about. So you have a general case, which I will not talk about. You have 2, which come from complex geometry. You have the other 2, which come from quaternionic geometry, and then the last 2, which are special dimensions, dimension 7 and dimension 8. I'll tell you a few more words about this. And then there was an extra one originally, spin 9 in dimension 16. But I think that was ruled out by essentially in the late 60s as being only only symmetric spaces, not and so for a long time, people have tried to figure out whether this list of possible harmony groups were actually realized, could actually be realized as harmony of Riemann manifold, compact Riemann manifold. Example, I'm not really sure, but I think the advocated case. I mean, the first example that I know, I think they come from a paper of Calabi in the late 70s, so more than 20 years after compact. So I don't know if all these groups were actually realized at the time of Berger's theory. Of course, as I said, for spin 9, that wasn't the case. Anyway, so the last 2, the spatial dimension 7 and 8, they come from the geometry of octonions, which you can see either in this table or in the final plane. There are different versions of writing them according to convention, but I'll stick to this one, which is not very good. And the structures on G2 and spin 7, they are basically, they have to be in a certain frame at each point given by these 3 forms. So in my notation, the upper indices is a way of denoting the extra product. So for G2, which is the set of automorphisms of the imaginary octonions, there's these special forms, which is the free form, and for spin 7, which is given by the only A-dimensional irreducible representation of spin 7, so it makes it a subgroup of right, is given by this 4 form. And if I go back to Berger's list, you can see that to each of these examples corresponds formulations in terms of parallel tensors. So in the case of Taylor, it's well known that the almost emission structure has to be parallel, and Calabi-Yau, you have the same condition plus homomorphic end form, which has to be parallel, and same thing for the other 3 cases. In G2, the form that I've just shown you, the 3 form that I've just shown you, has to be parallel with respect to the Levi-Civita or connection of the Riemannian manifold that started from, and same thing for spin 7. So these, why study harmony, apart from trying to figure out whether Berger's list contains some imposters or not? First of all, is that homology is a Lie group, and it tells us information about the curvature tensor. So the curvature tensor is the Lie algebra, and so for some cases, SU n over 2, SP N4, G2, and spin 7, that implies that it's Ricci flat. So that could be seen as a way of finding Ricci flat value. There's also a reason we're linked to gauge theory. So for example, here I try to explain what gauge theory for G2 is. So you start from the 7-dimensional manifold, you consider all vector bundles, you take a collection of these vector bundles, and you compute this curvature, which is a 2-4. And you want to reproduce in dimension 7 what you know about dimension 4, and work with Donaldson, for example. You want to compare the Hodge of the curvature with the curvature itself. But of course, this equation here is impossible because on the left-hand side it's a 5 form, on the right-hand side it's a 2 form. So you need a 3 form to sort make them possibly equal. So the equation becomes in here, and you need these 3 forms on that 7 manifold. And then you want to close as well. In particular, if you take it parallel, it will be closed, so that you can link them to Yang-Mills connection. So in case of G2, these parallel 3 forms would be a way of reproducing Yang-Mills and Donaldson theory in dimension 7, and same thing for the other cases on the list. Edges theory. And the problem is that to find such parallel forms is difficult because there's actually a dependence of the connection on this tensor that you're trying to make parallel. So this is a really non-linear equation. It's really difficult to solve. In particular, the same for G2. Originally, it wasn't clear for almost 30 years whether G2 should be on the list or stripped out. The first local example was due to Bryant in 1984. Then the complete example was a couple of years later, and it's only really with Joyce. The hard analysis that the compact example. So what we call the geometric structure, as in the title of my talk, is the weaker version. Essentially, trying to find tensors as in the list of Berger, but without requiring the fact that they are parallel. And there are different ways of introducing geometric tensors, but essentially they are tensor or a family of tensors. It could be a few of them. And we simply require that the general GLN action on this tensor, on Rn, psi 0 is on Rn, is stabilized by the action of the subgroup H, which could be any of the list on Berger's dot. And we simply ask them that it stabilizes the model tensor psi 0, and then an H structure on the remaining manifold, which would simply be a tensor with a frame identifying it at each point with the model we've taken up on the I won't think smooth, as I said at the start. And you can see all of this in more general cases as a reduction. So take Q to be the SUN principal bundle instead of OA. And then you can, the existence of such a structure is equivalent to the existence of a reduction into an H principal bundle, which is the same thing as found in the section of this homogeneous bundle, which is the quotient of the principal SON bundle, by the group that you've decided, the subgroup of SON that you've decided to work with. There are different ways of stating the same thing, as very often in math. So this is a section of this quotient. This is the reduction of the structure group, and there is also a 1-1 correspondence between an H structure and an H class of frames. Now, if you pick a particular group, then you could have a different interpretation. So if you take H equal UN, then you read N, the quotient of the principal of of the principal bond load of a normal frame, quotient by UN, is the usual twistor space of it. If you take G2, then you can actually explain that this is a bond load of fibers at RP7, and it's actually the same thing for spin 7. Now, the question is, in this construction of quotient and section, the question is whether you can find sections of it. Now, for example, this question could be answered by purely topological criterion, for example, in the case of G2, and simply have to be orientable and spinable. But if you take H equal UN, there is no topological condition on the manifold that would guarantee that the twistor space admits a section, a global section, and global continuous section. So all of these groups, we try to treat them together, but all of them will have their own characteristic, their own property. Now, if you drop the condition of being parallel, and just talk about reduction of the structure, then you can actually include in the list things that were outside of Belgium. For example, you can include almost contact structures by taking an odd-dimensional manifold and reduce the UN to the identity. Take H to be the identity, then you get global orthonormal frames. And then if you take SOM and do SOM plus 1, then you get a unit vector field. And then you can pick any subgroup, whichever you want, subgroup of SOM, and apply the machinery and apply this reduction, etc. Maybe there will be no section. If there are, then you can do as we did in the rest of the flow. Now, harmonic math, Stefano Montano talked about harmonic math this morning, so this is a much more general theory between two relying manifold. I assume the domain is compact, so there's no problem, no question about integration. You define the Dirichlet energy and you look for critical points. So this is very standard and very general statement. You can write the Euro-Lagrange equation, and you have lots of very nice properties that have been used a lot, studied a lot over the last 60 years. Stefan also mentioned EOSAT and Cerebro 64. Now, as he said, what they prove essentially is that if the target has negative curvature, then you can always find a harmonic representative in each homotopy class. Now, what they used to prove this is a geometric flow. Now, we know nowadays that geometric flows are important, especially since work on the Ricci flow and the Poincaré conjecture, but at the time it was probably the first appearance of the geometric flow method. Here it's quite important, of course, the curvature, because, for example, not only there are counter-examples to this theorem when the target has positive curvature. In the case of degree 1 map, so that's one homotopy class. And for example, if you look from map from S2 to S2, it's well known that's due to Sachs and Mullenbeck from 40 years ago. Well, they studied the flow, and from S2 to S2, they know that the flow explodes. They have a procedure of conformal change of variables, so they can start to get in the flow, and in the end it converges, but this is very complicated. On the other hand, if you want to find a harmonic maps in some homotopy class from S2 to S2, it's very simple. Take a polynomial with Z. Now, in our particular case, what we want is to go back to our sections that I mentioned, reduction of the structure, sections into this sort of generalized twistor space, and apply the theory of harmonic maps. Now, because it's a section, of course, a section takes a point to the point itself, and a section in the fiber. When you compute the energy, the Dirichlet energy, there is a constant term that comes from the horizontal frame, the horizontal part of the tangent frame. So, we will concentrate on this, but this part has no constant, which sometimes we call the vertical energy. And apart from this constant, we take the energy of harmonic math, but more importantly, what we want is to take variation of this energy, with or without the constant, I don't care, but through sections of the bundle. So we don't want to take variations through maps, because if you do this, you're not comparing structures with structures, you're comparing structures with maps. So you lose the geometric meaning of being a geometric structure. So we want variations of this energy, but only through sections of the bundle. Now, we assume that the Lie algebraic composition is reductive, which is, I think, at least in all the cases that I know of, this is the case. And this question of taking variations through sections of the bundle simply says that the delta for me is ddt over t, ddt at t equals 0. So it means that the tangent vector to the variation has to lie in this isotropic component with the length. So which essentially is the vertical part of the tangent space of my twistor space. To describe it better, we introduce this diagonal operator, which is an infinitesimal delta scale ddt of the action of the leaf group and of the GNN action. And in the case of each group, well, you can actually, of course, write down what this isotropic term is. So in the case of K manifold, if you want H equals UN, well, the other isotropic, the orthogonal to UN, is matrices which anti-commute with K0. For G2, well, you can characterize them as two forms. It's a 7-dimensional space. And you can calculate them as two forms, which are some sort of eigenvalues of a certain operator. So omega is a 2 form, phi is a 3 form. The range of them is 5. You start, you get a 2 form. So this vector. In 7, you have again a description in terms of 2 forms. It's still 7-dimensional. Spin 7 and G2 are not in common. And again, this is a fairly similar formulation of this isotropic component form. But in the case of SUN,
eigenvalue, I think 21-dimensional.
That's the algebra. That's the algebra spin 7. Split SOA into the algebra spin 7, which is the one we were talking about, and the isotropic component, which is
the other one is not.
Now, the isotropic means that it's a complement to the algebra base. And so SUN, this component that I call the isotropic component, it actually splits into irreducible, N1 and N2. And remember that in SUN you have two tensors. You have the J of the almost complex structure, and you have this homomorphic volume form. So each one of these components corresponds to one of these elements. And one of them is N1 is the same as for UA, and the other one is trivially the one So here, more or less, you have the representation theory of each of the groups H. And each one of them will have its own properties, and in particular, that will have to be reducible. So that will be a bit more. Geometric structure. There is no problem. constant, I only get through section, that is and then
What is fixed here? The metric is the